Hello. Today we are going to see how to write electronic configuration of atoms in a simpler way. Starting with this topic, first of all, let's study how to write electronic configuration in general manner. So, the basic representation is NL raised to power x. What does this n means to us? So n simply means principal quantum number. N is principal quantum number. In the last class, we have already seen about these quantum numbers: principal quantum number, azimuthal quantum number, a magnetic quantum number, and spin quantum number. So n means principal quantum number, whereas this L, it simply means azimuthal quantum number. And this X means number of electrons in the subshell. All right. So this is the basic representation of electronic configuration of any atom. So let's see. Basically, there are two different kind of electronic configurations. One is the elongated part. The second part is the condensed electronic configuration. So let me start first of all with the hydrogen, the simplest atom, which is hydrogen atom. So it has only one electron. It means we have to fill the electrons in the 1s subshell to 1s1, right? We have already seen the rules of filling the electrons in the subshells by Aufbau principle, by the Hund's rule, by the Pauli's exclusion principle. In the videos, you can see the videos. It is already there. So hydrogen, there is 1s1. If we talk about helium, it is equal to 1s2. Then we talk about lithium. It's a three atomic number. So we have 1s2 and 2s1. All right. Now, see this very, very carefully. For this lithium, I can write condensed form as well. How can I write condensed form? Since 1s2 is the configuration of helium, which is a noble gas. All right. So we can easily write this in this manner also. In the square brackets, we can write helium, which is a noble gas. And then we can write the outermost orbital, which is 2s1. This is called as a condensed electronic configuration. This is condensed electronic configuration. All right. So if anyone asks you what is the outer electronic configuration, you can simply say this thing, that this 2s1 is basically outer electronic configuration. This is outer electronic configuration. So this is how we can write configurations in longer manner, or we can write configurations in the condensed forms. So this is how we can write it down. Let's keep on doing. Let's talk about the nitrogen now. So nitrogen, the atomic number we have is 7. So let's keep on adding the electrons. We have 1s2, we have 2s2, and 2p3. All right. Now you can see here the first two electrons is generally of helium. Means it simply belongs to the noble gas. So this part we can we can also write helium in the square brackets. Then we can write outer electronic configurations, which is 2s2 and 2p3. This is the ground state electronic configurations, right? So these are basically called as ground state electronic configurations. All right. So this is how actually we can write it down. We can write this for any atom we have, right? So nitrogen 1s2, 2s2, 2p3, or helium 2s2, 2p3, because 1s2 belongs to the helium, right? So we can write the long form as well as the condensed form, right? So now let's keep on adding, the elements. Let's go directly to the sodium right now. So sodium, the atomic number is 11. Can you help me write this electronic configuration? It's very easy. So let's start with the 1s2. Then we have 2s2, then 2p6, and now we have 3s1. So you can see very clearly here. Basically, now this previous, we can write it in the form of noble gases, and you know that what are noble gases? Noble gases, helium is 2. Then we have neon, we have 10. We have argon, we have 18. We have radon, we have 54. We have xenon, and it is 86. So these are the atomic numbers. We should remember all such things. Now you can see here, 1s2, 2s2, 2p6. If you count, it becomes equal to the neon atomic number. So can we write it like this? Or in the square brackets we have neon, and then we have 3s1. So this is the condensed form, and this is the elongated form. Very important. So we are just learning how to write electronic configurations in the condensed form or in the detailed manner. So can we write the basically the condensed form directly for chlorine? Can you help me do that? What is the atomic number of chlorine? Chlorine, the atomic number is 17. So now what is the preceding noble gas? So always look at that. What is the preceding noble gas? So preceding 17, we have neon, right? So we can directly start with the neon. It has 10 atomic number. Now 7 electrons are remain. So we have, because after neon, the third shell starts. So we have 3s2 and then 3p5. We can directly write it like this. So this is how we can write the electronic configurations in the condensed form or in the detailed manner like this. So let's do one more. Let's do one more. Can you help me write the electronic configuration of calcium? Anyone who can help me, the electronic configuration of calcium? So guys, calcium, the atomic number is 20. So what is the preceding noble gas? We have already seen in the table, the preceding noble gas is 18, argon. So directly write like this. In the square brackets, we have argon. Now after argon, basically fourth shell starts, right? So we have, after argon, we have only 2 electrons left. The answer is argon 4s2, direct answer. All right. So I hope this helps you basically writing electronic configuration of all these elements, right? Now, this is how we can write basically electronic configuration of S block elements. Let's take few examples for 3D series as well. Very important. Let's take a very good examples, guys. 3D series. Okay, because there are few exceptions that belongs here, and we can explain why these exceptions do exist, right? So in the 3D series, let's start with the scandium first of all. So what's the atomic number of scandium? It's 21. Let's keep on filling the electrons one by one. We have 1s2, we have 2s2, we have 2p6, then 3s2, then 3p6, and after that we have 4s2, then we have 3d1. So this is how we can write the elongated electronic configurations. Now you know that basically it has 21 atomic number. Preceding to that, we have argon. So up to this much, 3p6, we have obviously argon. Then we have 4s2, 3d1. So can I write this configuration as like this one? Argon, 4s2, 3d1. This is how we can write. Okay. So basically, this is a correct representation, or we can also write like this, because sometimes the shells are always written in the increasing order. Obviously, electrons are first of all filled in the 4s because it has a lower energy than 3d. But generally, it's a convention to write the lower shell first. So we have 3d1 and 4s2. This is also accepted. So both forms are completely accepted. So this is how we can write for scandium. All right, let's keep on doing. Let's keep on doing for titanium as well. So if I keep on doing titanium, atomic number is 22. Can I write directly now? Argon, we have 3d2, 4s2. Okay, 4s is already filled first, then 3d. But in while writing, we write in the increasing order. So first 3d, then 4s. Now help me doing the vanadium as well. Vanadium, the atomic number is 23. Now the configuration is argon, and then we have 3d3, 4s2. All right. Now, here comes a very, very important example, which is of chromium, atomic number 24. Now, if we keep on adding the electrons, one can write like this: argon 3d4, 4s2, right? But let me tell you, this is wrong. This is not accepted. Why? What is the logic here? Why there is a discrepancy while writing the electronic configuration of chromium? The answer is huge. The answer is very, very important. The answer is stability of half-filled d orbitals. Stability of half-filled d orbitals. Okay, stability of half-filled d orbitals. I'll explain you in in the next video what does this stability of a half-filled and fully filled orbital means to us, right? So basically, instead of doing this, it simply fill the electrons in a very different manner. So let me show you how this fills electron. So instead of doing this 3d4, it takes the one electron from this 4s. It simply accepts the electron from 4s, and the corrected form for the configuration is argon. It takes the one electron, guys, from the 4s, and it becomes 3d5 and 4s1. And this is the very, very important example. This shows us that chromium actually has deviated from its normal trend. So normal trend deviates whenever we have a stability pattern of half filled and fully filled configurations. We are going to see this, right? The same thing arises when we talk about copper as well. What is the atomic number for copper? Can you tell me that? Can you write in the chat box what is the atomic number for copper, guys? Copper has 29 atomic number, and if you fill the electrons, it would become like this: argon, right? We have 3d9 4s2. But like I tell you, this is again the wrong electronic configuration. Why this is wrong? Because again we have 3d9. It tries to get an electron from 4s to becomes fully filled d configurations, d orbitals. So we have argon 3d10 4s1, because one electron would be transferred from 4s to 3d9. It becomes this as the correct configurations for copper as well. So this type of discrepancies, why they arises, and what do we mean by this half filled and fully filled configurations, we are going to see that in the next video. Thank you so much.